Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. Today I'll be discussing a concept on bending stress in a beam. So basically what is a bending stress? So when an external load acts on a beam, the shear force and bending moment will be set up in all the sections of the beam. So, due to the shear force and bending moment, the beam will undergo certain deformation so that the material of the beam will offer some resistance or stresses against these deformations. So, these stresses with certain assumptions can be calculated, and the stresses which are induced by the bending moment are called as bending stress. So, the stresses which are introduced by the bending moment are called as bending stress. I repeated, whenever the external load when it acts on a beam, there will be causing the shear force and bending moment in all the sections of the beam. So due to the shear force and bending moment, there will be some deformation. So these deformations will be resisted by the material of the beam, so which causes the stresses. So these stresses which are introduced due to the bending moment are called as bending stress. So here you can just see here in the sketch that a beam initial position is straight. So when it is loaded with some load, so here in particular I have taken the uniform load of W magnitude. So whenever there is the application of the external load, the beam will bend along the direction of the load, so that there will be formation of the bending moment, and then which in turn results in the formation of the stresses. So that stress is called as bending stress. So here you can just observe the top fibers of the beam will be subjected to compression, and bottom fibers are subjected to tension, and there is a neutral axis wherein there is no tension or compression in the neutral axis. So this is all about the bending moment. So bending stress. So next is the concept of pure bending. So I have just considered a overhanging beam, that is in particular the double sided overhanging beam. So when a structure when it is applied with some magnitude of the load, then there will be resultant of shear force and moment simultaneously. So I have considered the beam here, wherein some part of the beam resulted to negligible or zero shear force, but some part of the structure the bending moment is maximum or constant variation. So therefore, pure bending is a condition of stress where the bending moment is maximum or constant. Simultaneously, the shear force or the torsional force is equal to zero at the same stretch, or it is negligible. So here you can just identify the overhanging beam, double sided overhanging beam. So here with on either side it is loaded with W magnitude of W both the ends. So here the figure B, second figure, represent the shear force diagram. So wherein the variation is W plus W and minus W at the overhanging part. So here again in the shear force diagram you can also observe that in the part AB, so in this position AB, so there is zero shear force. So simultaneously if you just observe the bending moment diagram here, so you have the maximum or the constant variation. So compared to the point D and point C, you have the bending moment which is more, and also its variation is linear, that is constant variation. So in the same stretch, that is at the stretch AB. So by this you can state that the pure bending is a condition of the stress wherein the bending moment is maximum or constant with the zero shear force or negligible shear force. So pure bending, I repeated, pure bending is at the particular length of the beam, so the bending moment is maximum or constant corresponding to the zero or negligible shear force. So here I have taken a overhanging beam AB is a simple supported part wherein by same length at each of the support it is shown in the figure. The point load W is applied at each end of the overhanging part. The shear force and bending moment are drawn here. So here from this diagram it is clear that there is no shear force which is there between A and B, but the bending moment between AB is constant, and this means that between A and B the beam is subjected to constant bending moment only. So this condition of the beam only between AB is called as pure bending, or it is also called as simple bending. So in this case the portion AB only experiences the simple or pure bending wherein the bending moment is maximum or constant but corresponding to the zero shear force or negligible shear force. So this is all about the concept of pure bending. So next, coming on to the assumptions of simple bending theory. So here while analysis of any of the element for its bending stress, so we are supposed to assume some statement based on the simple bending theory. So some of the important assumptions are, the first and foremost thing is that the material of the beam is considered to be homogeneous and isotropic. So the material is considered to be homogeneous and isotropic. So next is the value of Young's modulus of elasticity is considered to be same or constant in both the tension and compression zone. So the value of modulus of elasticity or Young's modulus is same in both compression and tension zone. So next is as in case of transverse section which were plane before bending, it remains plane even after bending also. So the sections which were plane before bending will be plane even after bending also. So next is the beam which was initially straight and all the longitudinal filaments bend into circular arc with common center of curvature. So initially before the application of load, the beam which was initially straight, so after the application of the load the beam starts to bend wherein in the form of circular arc with the common center of curvature. So next is as it bends in the form of circular arc with a common center of curvature, the radius of this curvature is very large compared to the other dimension of cross section. So I repeated, the radius of curvature is large compared to the dimensions of cross section. So next is each layer of the beam or any element will be free to either expand or contract independently to the other layer which is present above or below to it. So each layer of the beam is free to expand or contract independently of the layer present above or below to it. So these are some of the important assumptions regarding the simple bending theory. So next is neutral axis. So neutral axis, it is the axis which is present in which is passing through a beam at exactly at the centroid. So here you can the neutral axis will always experience zero stress. So zero stress, and it will be neither subjected to tension nor compression. So it will be neither subjected to tension nor compression. So neutral axis, it is the axis of the beam wherein it is subjected to zero stress, and it is having neither tension nor compression. So here you can just observe the diagrammatic representation here. So this is the initial position of the beam in the longitudinal section. So this is a cross section. So before application of the load, this was the initial position, that is a straight line. So after the load application, the beam will bend, so in such a manner that the upward portion of the beam, so this portion of the beam is subjected to compression, and this portion of the beam is subjected to tension. So here at the outer ends you can see it is represented by the arrow marks. So middle portion, you have a line exactly here, so wherein the line is called as a neutral layer or neutral axis. So wherein this neutral axis will neither be experiencing tension nor compression. So therefore the neutral axis will be having zero stresses. So neutral axis, it is an axis which is having zero stress and is subjected to neither tension or compression forces. So this is all about the neutral axis of the beam. Thank you for watching. Please like, share and subscribe the video. Thank you.